Common patterns in organic synthesis take 2. And we've got a couple more patterns to learn, but this time they're going to involve alkynes instead of alkenes like in the last lesson. And based on the reactions you have at your disposal, alkynes are going to be one of the more important ones at this stage of the game, because this is one of our big ways to make a carbon-carbon bond, as we saw when we looked at increasing the length of the skeleton back in the first lesson in this chapter. This lesson is part of my new organic chemistry playlist. I'll be releasing these lessons weekly throughout the 2020-21 school year. So if you want to be notified every time I post a new lesson, subscribe to the channel and click that bell notification. All right, so common patterns involving alkynes, and one is often, how do you make an alkyne? And back in the first lesson in this chapter, we learned that there's one major way to make an alkyne, and that's to turn a geminal or vicinal dihalide and just do 2 rounds of E2 elimination with NaNH2 as your strong base. So one of the things that often trips students up is they start with an alkene and then realize that they're supposed to turn this somehow into an alkyne, and they're like, well, we make alkynes with NaNH2, and they just write NaNH2. So, well, again, that works as long as you're starting with a geminal or vicinal dihalide, which we're not. So if you have no good leaving groups here, well, then you're not doing E2 elimination. And so this is not going to happen in one step here. It's going to take a couple of steps. And so first thing you're going to need to do is somehow convert this into a vicinal or geminal dihalide, and it just so happens that we know how to turn it into a vicinal dihalide here. So and in this case, that's going to involve Br2 and an inert solvent, your alkene addition reaction, and that could be CH2Cl2 or CCl4, carbon tetrachloride, either one for your inert solvent, and it's just going to add Br to both sides of the alkene here. So, and now that you've got 2 leaving groups, you can do 2 rounds of elimination, again using our new favorite strong base in the alkyne chapter. So excess NaNH2 followed by water to protonate. And so now we've made our terminal alkyne. And so question is then, well, what do you do with the alkyne? Well, it turns out there's a lot you can do with an alkyne, and but in this case I want to focus just on adding a carbon chain to the other side of it. That way we can kind of see the last part of this common pattern. But in the next pattern, further in this lesson, we'll look at some of the other possibilities as well. So, but in this case, to add a carbon chain to the other side here, we got to first turn this into an acetylide ion. So we need to deprotonate terminal alkyne, form that acetylide, and then we can add the appropriate alkyl halide. I'll just add a 3-carbon alkyl halide. Just key is making sure that it's methyl or primary, not secondary, or else E2 would become more likely. And in this case, then we've now added 3 additional carbons to the other side. So 1, 2, 3. We've got this lovely species here. So notice I put these 2 together, and you'll often see it presented that way, NaNH2 in step 1 and the alkyl halide in step 2. If you split it up into 2 separate steps, not a problem. So if you want to actually show the formation of the acetylide ion and then have it reacting, so great. But oftentimes you'll more commonly see it actually presented in a single kind of synthetic step, if you will. All right, but now that we've got this lovely species here, we've really got 3 options that you've learned somewhere along the way, and 3 different alternative reductions, and giving 3 different results for an internal alkyne. And that's why they show up so commonly in synthesis, is that with 3 different results, you really got to know your reagents. And so your options here, you could just use catalytic hydrogenation normally. You could use catalytic hydrogenation with Lindlar's catalyst, a poison catalyst. So, or you could do dissolving metal reduction like sodium in liquid ammonia. And so in this case, if you just do general reduction, you'll reduce this all the way to an alkane, 1, 2, 3, 4, 5, 6 carbons. So 1, 2, 3, 4, 5, 6 carbon alkane, life is good. Now, if you do this with H2 and Lindlar's, you'll reduce it to a cis alkene. And so I like drawing the alkene first and then making sure it comes out cis. And so I've got this carbon here, and I need 2 more carbons on this side. So, but if you use sodium and liquid ammonia, dissolving metal reduction, it'll go trans instead. Cool. And so this, again, why this becomes a common part of synthesis is that you've got 3 different results starting from this point. And again, it's just a great way to make sure that you as a student really know your stuff, because I can put any one of these as the desired result, if you will. So let's take a look at an example of this. All right, so our example here, we're starting with an alkyl halide and trying to end up with a terminal alkyne here. So we're going to avoid any kind of one of these last steps in this example. So the question is, though, how do we make that terminal alkyne? And we know that our carbon chain is bigger than the one we start with, so we know we're going to be doing something involving an acetylide ion. It's the only real way you know at this point to significantly increase the number of carbons in the chain. And if you're going to involve an acetylide ion, that means you have the potential to make either this bond or this bond. So, and the question then becomes, well, where do these three carbons match up with this? Because the truth is you got some different options, right? It could be 1, 2, 3 carbons. It could be 1, 2, 3 carbons. It could be 1, 2, 3 carbons, or it could be 1, 2, 3 carbons. All of those are possibilities. So the question is, well, where are these 3 carbons? Well, that depends. So there is a version of this question that says, make sure that all of the carbons in your product come from molecules of this only. Well, that would kind of suck. So, but it is possible. It would just be a lot of steps. So, but the truth is, if you look at the bonds you can make, so making this one and having 1, 2, 3, 4, 5 carbons on this side and just 1 carbon on this side would make it very difficult to get the, either one of those structures, truth be told. So, but if you consider making this bond right here, you got 3 carbons on one side, 3 carbons on the other side, which would be really convenient if you're starting out with a 3 carbon organic molecule here. So the question is, which way could you do it? Well, the truth is you could do it either way. So, but if we look at this in a retro way, in this case, you can see that going this route, you really are going to need this guy, and then you're going to need to add NaNH2 and this guy, which happens to be the thing that we started with. And so one way the synthesis could work, and this would be the easy way, is you could just say, well, actually, I'm going to start it from my corresponding alkyl halide, and I'm just going to add this. So in fact, I should write that in red to be consistent with what we're doing. So, and voila, we're done. So life is good. It would be a one-step synthesis. So, and the truth is that would be actually totally acceptable. However, if we said that every carbon in your product has to come from this guy, well, that means if I got 6 carbons in my product, then I'm gonna have to use 2 of these, which means this is not gonna quite be acceptable. So it's cool that we got this guy, but that means these 3 carbons have to be built from this guy as well. And so if we kind of take that approach here, so these 3 carbons were cool. That's our reactant. Life is good, but we need to make this alkyne as well. Well, how do you make an alkyne? Well, again, we don't have an alkyne to start with, so how do you make one? Only way you know how to form an alkyne is from a vicinal or geminal dihalide. So we should go back and here a 3 carbon, and vicinal is much more common. So in this case, again, you'd use excess NaNH2. Followed by water. So question then is, well, how do you make a vicinal dihalide? Well, you make a vicinal dihalide from an alkene. So, and again, that's Br2 in your inert solvent. So, and instead of using CH2Cl2, I'll use the other common inert solvent, CCl4. And the question is then, well, how did you make an alkene? Well, alkenes are made in E2 elimination reactions, and we just need a lovely strong base. And with a primary halide, we want to make sure we use that bulky base. So that way SN2 is not going to be a major competing reaction. Cool, and this would be your synthesis. Notice this is quite a few steps. We've got step 1, step 2, 3, 4, and this is getting to be a rather long synthesis problem, even at 4 steps. And like I said, 2 to 5 is pretty typical, but really 2 to 4 is the most common. And by the time you get to 4, like this is really pushing it for most classes. So most professors are usually going to be a little bit nice, and you'll find out that a lot of synthesis, especially early on in the second semester, are going to be of the shorter varieties. So this one's pretty long, but still totally acceptable. All right, so the other common pattern in synthesis involving alkynes is going to have you potentially starting all the way as far back as just plain old acetylene. And what's nice about acetylene from a synthesis perspective is that you can form a carbon-carbon bond on either side or both sides of this alkyne. So, and if you want to do it the first one, so and let's say that your goal really is to do both sides. Well, again, first thing you're going to do is use NaNH2 to deprotonate it. Oh, let's do this in red. My bad. Let's keep this consistent. So we're going to use NaNH2, and that's going to form our acetylide. And again, you can only form it on one side at a time. You can't deprotonate both sides at the same time. So we'll deprotonate one of these sides, and we'll form acetylide on one side. And those acetylide ions can attack either alkyl halides, SN2, or a ketone or aldehyde. Or an epoxide. And the key is when you actually attack either a ketone or aldehyde or an epoxide, you're going to form an alcohol as a result. And that alcohol is problematic for these reactions. It turns out once you have an alcohol in the molecule, you actually can't form, you're going to have trouble forming the acetylide again and doing the reaction you think you want to do. And so if you look at the two things you're adding, if one of them is involving attacking an alkyl halide, the other one is either a ketone aldehyde or attacking an epoxide and has an alcohol, you've got to make sure that the one that forms the alcohol happens last. Super imperative, as we'll see in a second. So in this case, I'm going to take and generically say that we're going to use this guy. I'm going to make this any kind of carbon chain, and I attached them to a CH2 group and then a Br. That way this is a primary halide, because we really want to make sure this is either methyl or primary for this to work. So, and in this case, that's going to get us to this guy. So, and I could have added it to either side. I just chose the left. So life is good. Question is, okay, then what do you do from here? Well, from here, now that you've got an alkyne, you've increased the carbon chain, it's a little bit bigger, so you've got quite a few options at your disposal. And so the question is, what are you going to do? Well, you could add something to the other side, and you've got three options for that possibility alone. So let's take a look at those three options. So option number one here is you could use NaNH2. So, and then another alkyl halide of some sort. So in this case, we'll call this R prime. So, and make it primary yet again. So, and in this case then, we'd have something out of the other side now with an R prime. You just add an alkyl halide to both sides. Okay, life is good. So once we've done that, you could potentially consider reducing this either with catalytic hydrogenation with a poison catalyst like Lindlar's, or dissolving metal reduction, either to turn this into an alkane, a cisalkene, or a transalkene, but very similar to what we've seen before. But those are on the handout on your table, but I'll leave it out. It's just like the pattern we saw in the last section here. So your next option would be to, again, deprotonate with NaNH2, form your acetylide, but have your acetylide attacking a ketone or aldehyde. So, and this was the aldehyde we used, but it could be any ketone or aldehyde in principle. So, and then some dilute H3O+. Some people use water here, just FYI. So use whatever your professor happens to use. All right, so if we did this in this case, so we'd attach to this carbon right here, which is now that carbon. That carbon's still going to be bonded to an O, and then it's still going to have this one other carbon here. So there's the new bond we formed. So, and in this case, then the O gets protonated, becomes an alcohol. So that's our next option. Cool, we've got another option here as well. And instead of attacking a ketone or aldehyde, we can attack an epoxide. So we got, again, NaNH2 to form the acetylide. Now we'll take an epoxide. And once again, we have to protonate the alcohol that forms with either water or H3O+, depending on the preference of your professor. So in this case, you're going to attach to one of these two carbons, but it'll be the second carbon out that actually is bonded to the OH. Not the carbon you attach to, but the next one over. And big thing you're going to be on the hook for in recognizing which of these options you actually did when you're actually examining a product. So, because we always know that, we can make the carbon adjacent to the alkyne through an acetylide ion. If the carbon you're attached to is bonded to an OH, that's evidence you attacked a ketone or aldehyde. If it's not that carbon, but the next one down the chain that's bonded to an OH, that's the evidence that you attacked an epoxide instead. Okay, what other options do you have? Well, you've got all those lovely alkyne reactions you guys did as well. And so you guys did like HgSO4 and H2SO4. And if you recall, we got what, 1, 2, 3 in the R. So here, 1, 2, 3. So, and that's going to go Markovnikov and tautomerize and get you a ketone. So it originally forms that enol, tautomerizes to the ketone, but the oxygen is on the more substituted of these two carbons. You could also go anti-Markovnikov with hydroboration oxidation. Oh, typically we'll use a bulky borane, so you could use BH3, but you'll often more commonly see some sort of bulky borane like dicyamylborane here. Oh no, I was meant to write these in red, and I'm still writing them in black. C'est la vie. And being anti-Markovnikov, now the carbonyl ends up on the end carbon, and you get an aldehyde instead. So, or we could take this one step further, and maybe we do ozonolysis. So an ozonolysis is going to do that oxidative cleavage, where we'll cleave this, and if we have one carbon on the terminal, it's going to be CO2, and the other side will be a carboxylic acid, so we'll have our R group, and then two more carbons and a carboxylic acid, so R group, two more carbons and a carboxylic acid, and technically carbon dioxide as well. Cool. And this is kind of your common patterns in synthesis. You turn acetylene into a more complex alkyne, and with that you can do one of your normal alkyne reactions, or you could then deprotonate the other side and attack something else. But once again, if you do end up trying to form something along the lines of these guys, where it does involve attacking either ketone or aldehyde or epoxide and you form an alcohol, that has to happen second. If you, let's say for a second, let's just say you attached the right-hand side first. So then when you went to go use NaNH2 to deprotonate the other side of the alkyne, it would actually deprotonate the oxygen, and you'd have some competing issues going on in the next step. So it would be actually a big pain in the butt, not going to get a good yield of what you want to, or any yield depending on if you don't add enough NaNH2. And so it's just a big no-no. And so if you've got, you start out with plain old acetylene, and you want to attach a carbon chain to both sides, if one of them is through the alkyl halide, you've got to do that first. If the other, if one of them involves an alcohol, that has to be the second of the two that you actually do. All right, so let's take a look at a couple examples involving this pattern here as well. All right, so we got two examples here. We'll start with this top one here. In this case, I'm starting with plain old acetylene, and I can see that these two carbons, in all likelihood, are probably the still two that are involved in having a triple bond, although that's no guarantee that it has to be that way, but it's commonly going to be that way. And so I'm just going to kind of make that assumption. If it doesn't work out, well, then we'll try something else. So I'm going to assume that these two carbons match up with these two carbons, and that means that I need to make this carbon-carbon bond right here and this carbon-carbon bond right here. And once again, if I've got to make carbon-carbon bonds on both sides, if either side has an alcohol, then that's the last one I have to do. And so in this case, I can work my way backwards and say then I must have started this step already having this side attached, because this is the side that has to go on last. So, and in this case, the first thing I do is form the acetylide ion with NaNH2. And then what's the other reagent? So a couple different ways to look at this. So you could say, draw this guy out before the bond was made, before we made this new bond. If I get rid of that bond, then this carbon right here would have a plus charge now. And you could look at it and say, well, one of the things we could do to avoid him having a plus charge in the real reagent is form another bond from the oxygen. And if we form another bond to him from this oxygen here and get rid of the hydrogen to make room, we'd have an epoxide. Other way you could look at it is it's not the carbon that we end up bonded to that has the OH, it's the next one down the chain. And that's the pattern that you should recognize to say that you formed an epoxide here. And so in this case, step 2 is going to be an epoxide, but our epoxide is going to have 3 carbons, not just 2. And so it doesn't really matter which side you add this to. So we're always going to attack the less substituted side anyways. So, and then you got to protonate, which again is either H3O plus or water, depending on the preference of your professor. All right, so that gets us the last step. And so then, then we got to add this side as well. And this side is just an alkyl halide. And so we did once again add NaNH2 to deprotonate and form our acetylide. So, and then we'd add the appropriate alkyl halide, which in this case would just be a 2-carbon alkyl halide, like this guy. So, and that would take us all the way back from acetylene. And so that's actually the entire synthesis. So it looks really complicated. You go from 2 carbons to this big giant structure. So, but it can be represented with just 2 synthetic steps. And again, you could split each of these out into 2 steps each and make it 4 synthetic steps. But the truth is, most of the time we would look at this as just being the equivalent of 2 synthetic steps. All right, so let's look at the next one here, and this one's a little more complicated. So what you can notice, though, you want to match up your reactants to your products, and you see that you got 4 carbons to start with, and you end up with 1, 2, 3, 4, 5, 6 carbons in your final result. We need to increase the length of our carbon chain. And at this stage of the game, you've learned one major way to increase the length of your carbon chain, and that is through an acetylide ion again. And so in this case, at some point, we're going to have a triple bond somewhere. Also, you got to recognize that we're trying to form a ketone on that carbon right here, because we definitely don't start with anything resembling a ketone. And we'll learn some new ways to make ketones in the future, especially in the next chapter with alcohols and stuff. But for now, you know one major way to make a ketone, and that's from an alkyne. Either Markovnikov or anti-Markovnikov, depending on its location and stuff like this. So if that carbon's going to end up with a double bond to oxygen to make a ketone, then you had to have an alkyne in one of the adjacent positions. Let's consider both of those for a second. So let's consider it 1, 2, 3, 4, 5, 6 there, or let's consider it at the end as well. 1, 2, 3, 4, 5, 6. So it could be either one of these. So if you look at it from the terminal alkyne, this would be considered Markovnikov, and we know how to do that. That'd be HgSO4, H2SO4. But if you look at it from this side, so here, these 2 carbons on an internal alkyne, they're equally substituted. And so it doesn't matter which reagent you use, whether you use HgSO4, H2SO4, or do hydroboration oxidation, you would get this product, but then you'd also get the carbonyl on this carbon as well, and get that product as well. And so starting from here, you're not going to get as good a yield of this one because you're also forming this one with roughly an equal likelihood. And so this is not as great of a method to get there. But here we totally know how to do this. So, and in this case, we would use again HgSO4, H2SO4 to pull that off. Well, the question is, well, then how do we make this? And again, we've got these 4 carbons. We want to make these 6 carbons. And at some point, we have to make the alkyne and stuff like this, but also we're going to have to actually form a carbon-carbon bond here to go from 4 carbons to 6. And in this case, the bond we know that we can form is that one right there. And so the question is, where do these 4 carbons, in all likelihood, mesh up on this structure? Well, again, if I'm making this bond, it splits it up into a 4-carbon fragment on the left and a 2-carbon fragment on the right. And so these 4 carbons, in all likelihood, are that 4-carbon fragment on the left. But we don't actually have to get there yet. We just say, well, how would I have made that bond? Well, okay. How would you have made that bond? Well, in this case, you would have started with the acetylene. You would have used NaNH2. So, and then you would have used 1, 2, 3, 4 carbon alkyl halide. So 1, 2, 3, 4, and a halogen. Great. So that's how we would normally have written it out. The problem, though, is that I actually am starting with this guy, and this guy's not going to make acetylene. This guy's actually going to make the alkyl halide instead. In fact, I know how to make this alkyl halide. It would be involved adding H and a Br, anti-Markovnikov, which we know how to do. So as a result, though, we can't actually represent this way because I have to show the succession here of how we get from here to what I draw right here, and that's where this guy needs to go because that's what I'm turning him into. And so instead, we've got to rearrange this a little bit and put him there. And instead, we've got to take our acetylide and make him the reagent, and we're actually going to add it in ready-made as the acetylide. I mean, technically, you could, start up here and, show this. But relative to our starting material, I'm just adding a ready-made acetylide whenever we need to this alkyl halide. Well, the question then, well, how do you form this alkyl halide? And once again, that's the addition of H and Br anti-Markovnikov, which we pull off with HBr and ROR. So a couple things you'll note. So we worked this backwards, straight up retrosynthesis. And also, when you've got to deal with leaving groups, you'll find out that bromine is way more common than chlorine or iodine or anything of that sort, just because free radical halogenation, bromination is more selective. And then also with HBr, we can do it Markovnikov or anti-Markovnikov, whereas with HCl and HI, it's only Markovnikov. And so if you're dealing with like, well, what leaving group should I put somewhere? Almost undoubtedly, it's going to be 99% of the time, it's going to be bromine, just an FYI. Cool, but this is your other synthesis problem, and once again, it looks long, and this one's really difficult because we are increasing the carbon chain and stuff like that. It's tough to match up these 4 carbons to the 4 in the product, but 1 step, 2 steps, and it is only a 3-step synthesis. So, but this is kind of boring on the edges of kind of how hard you could expect something to show up on an exam on this material up to this point. And like I said, in the next chapter, we're going to start learning about alcohols and ethers and epoxides, and we're going to learn more reactions that we can now start incorporating into this. We'll learn other ways to make ketones. And what you'll find is this, as we go further and further down the road in synthesis, you're going to find out there's not one way to typically carry out a synthesis. So, and as long as the 2 different routes take approximately the same number of steps and both give good yields of the products, so then often you might have more than one acceptable answer on a synthesis problem. So, but for now, we're restricted by just the sheer number of reactions we know up to this point. It's not a lot. So, but the more we add as we go further and further along, the more options we'll have, and we'll find out that, again, many synthesis problems will have multiple options. Once again, I said this in the last video, but if you do have more than one option to form, to carry out a synthesis, if one is significantly lower in steps, like at least 2 steps lower, that's the preferred method. Don't do the longer one. So also, if like you run into an issue like with this one where I was choosing between these two, this one would have formed this product and this product in roughly equal amounts, and so it's not going to give a good yield of just the one we want. So sometimes that's unavoidable, but in our case, we did have a way to avoid this, because in this case with the terminal alkyne, we could go the Markovnikov route and get this as the major product, the single major product. So life was good. So just keep that kind of thing in mind as well. But hopefully I've given you some food for thought on synthesis. Now you've just got to do a ton of practice. This is going to take some time. But hopefully we've laid a pretty good foundation for you. And like I said, we will revisit this topic almost every chapter throughout second semester. Once we learn a new functional group, we'll find out how are some of the common ways it gets incorporated into synthesis problems. Now, if you found this lesson helpful, would you consider giving me a like and a share? A couple of the best things you can do to help promote the channel. If you're looking for study guides, practice problems, practice final exams, or anything of the sort, check out my premium course on chadsprep.com.